So we're going to talk about gravitational fields today. So what do you mean by a gravitational field? It's actually a region, a space in which a force can be exerted on a mass. So if you have a mass, let's say here, right? And this is the Earth's surface, and let's say on top of the Earth's surface, we have a certain mass m in a certain space, right, above the Earth, right? So if you have mass m, this mass m is attracted towards the Earth, right? So it's experiencing a certain force towards the Earth. So this I can represent as the force due to gravity. This mass m is experiencing a force due to gravity. So this space here is actually the gravitational field, right? So in this space, this mass m is experiencing a certain force. Now remember, between two masses, right? So between two masses, there are gravitational forces. Between you and me, right? Between two objects, any two objects that possess a mass, you have a gravitational attraction. It's actually an attraction. Gravitational forces are always attractive forces. Always attractive forces. Now, if you talk about electric fields, and if you find a positive charge and a positive charge, the two positive charges are repulsed from each other. But if you consider two negative charges also, they are repulsed from each other. A positive charge and a negative charge, they are attracted towards each other. But if you consider masses, the masses are always attracted towards each other. So gravitational fields, if you talk about gravitational fields, you talk about attractive forces between masses. A very important observation. So what if I ask you this question, right? So if I ask you, how do you know there is a gravitational field? Like you want to test, okay, let's say you choose a certain region in a certain space, there's a certain space, and you want to know if there's a gravitational field there. So what do? You just place a mass, right? A certain object of mass m, you just place it there and see if that mass m experiences a force. So in that space, if you like exclude any other things like magnetic fields and electric fields, all the rest of it, if you just remove that, and then if you think about that mass m, if it experiences a force only due to the gravity, then there is what? A gravitational field there. Now think about this. Let's say I have a mass m and it experiences a gravitational force of F, right? So I have the mass m, it experiences a gravitational force of force F. Now we define something called the gravitational field intensity. Very important. Gravitational field intensity. So I remember this intensity as how intense it is, right? So it's just related. So gravitational field intensity, what is that? Now let's say I have a point A. In that point A, I take a certain mass and place it in that point A. And then I realize that the force experienced by that mass is F. Now the gravitational field intensity, listen very carefully, the gravitational field intensity at A is defined as the force experienced, the gravitational force experienced by 1 kg that I place at A, or rather the force experienced by a unit mass that I place at A, right? So the gravitational field intensity at A is the force experienced by 1 kg that I place at A. So, you know, a force of F was there for a mass of m, right? Or rather I can represent it like this. So for a mass of m, the force experienced by the mass of m is F. Then what is the force experienced by 1 kg? It's going to be definitely F over m, right? So the force experienced by 1 kg is going to be F over m. So then F over m is defined as the gravitational field intensity, right? I can just put it as E, the symbols don't really matter, but the gravitational field intensity E is equal to F over m, right? Okay, so I think that's clear. So if you look at the units, you can clearly see force is measured in newtons and mass is measured in kilograms. So the electric field intensity, sorry, the gravitational field intensity is measured in newtons per kilogram, right? So how many newtons per kilogram? That is the gravitational field intensity. Now I'm asking you this question. what do you mean by the weight of an object? What do you mean by the weight of an object? Now, you know, the mass, you can say it's m, right, in certain kilograms. But the weight of an object is the force of attraction or the gravitational force that the object experiences. That is known as the weight. Now, let's say there is 10 kg, right? And this is the Earth's surface, there's 10 kg. So what's the mass of the object? It's 10 kg. What's the weight of the object? 10 into 10. If it's the Earth, you just take it roughly, the gravity, to be 10 ms minus 2. So you see, F equals ma. I can apply that downwards towards this mass, right? So if we consider the mass of 10 kg, and if I apply F equals ma to 10 kg, what's the mass of this object? That is 10 kg. What's the acceleration of this object? This object experiences an acceleration due to gravity. That is going to be 10 ms minus 2. Therefore, you get F equals 10 into 10, that is 100 newtons. This 100 newtons is known as what? The gravitational force, which is also the weight of that object, right? So you have to understand these concepts. So now we are going to come to a very important definition or a law, Newton's law of gravitation. Now, what did Newton mention in his law of gravitation? So he said, if you consider any two particles in this universe, right? You just consider any two particles you like in this universe. Now, if you consider those two masses, right? Let's say m1 and m2. These are the two masses that you picked in this universe, right? These two masses experience a gravitational force, right? So mass m1 is attracted towards mass m2, and the mass m2 is attracted towards mass m1, and the attractive force is the same, something mutual. So mass m1 is attracted towards m2, m2 is attracted towards m1, and the forces of attraction is F and F, right? It's the same. So this force of attraction, Newton said, is directly proportional, he said it's directly proportional to the product of the masses. And he said this force of attraction between the two masses is inversely proportional to 1 over the distance between them squared. To 1 over the distance between them squared. Right? Is that clear? This is quite intuitive, isn't it? Like, higher the masses, right? Greater the product of the masses, greater the attraction. Now just think about the sun and the earth. Huge mass for the sun, and you know, somewhat considerable mass for the earth, and therefore the earth is attracted to the sun. Right? I'll tell you how these things are occurring. Okay, like I'll tell you why the earth goes around the sun and stuff like that, how it's attracted to the sun, and yet it's going in an orbit. I'll talk about these things later. But for now, just understand, when the masses are huge, when the product is large, the force is considerable. The force is considerable. Okay, so it's a notable force. So now, when I'm developing an equation from a proportionality, so I can say force is proportional to the product of masses divided by the distance between them squared. So then I can replace this by putting the universal gravitational constant. G is known as the universal gravitational constant, right? That into m1 into m2 divided by r squared. Now note that this G is a very small value. It's like 6.67 into 10 to the power minus 11 Newton meter squared kg minus 2, right? It's a very small value. Now you can understand why, like if you consider your friend and yourself, between you two, why aren't you all attracted to each other? In the sense, like through a gravitational force, not by any other means, but just through a gravitational force, right? Why aren't you not attracted? Why aren't you attracted? So if you have your friend of mass m and you of mass m2, why aren't you all pulled together, right, towards each other? The thing is, this G is very, very small. So just think, if this G is very, very small, right, just do a calculation and see. Let's say 6.67 times 10 to the power minus 11 is the value of G, and let's say your friend has a mass of 65 and you have a mass of 70, and the distance between you two is like 1 meter. Then I can take that squared, right? So 1 squared. So if you calculate this, you'll find out it's a very, very small value. Something like 3.03 into 10 to the minus 7, something like that, right? So you can see it's a very, very negligible value. It's a tiny, tiny value, but remember the fact that it exists, right? So how would you get a considerable value for the force? Now, if you consider the mass of the sun, I'm asking you to do this at home. Just find the mass of the sun, find the mass of the earth, and find the distance between the earth and the sun, and see if the force is considerable, right? So substitute the mass of the sun, substitute the mass of the earth, and the distance between them squared, and then you can find the force of attraction between the earth and the sun, right? You realize that greater the mass, okay, that means I'm referring to like greater the product of the masses, like M1 and M2. If the product is high, what's going to happen? The force is high. And also remember if the R value, which means the distance between the two masses, is low, greater the attraction. You see, F equals G M1 M2 over R squared. So when R decreases, what happens to the force? The force increases, right? It's very simple. So remember again, I'm just mentioning this again. So even though the forces are different, you can see that they're attracted with the same force, because it's so obvious. Because for each of these objects, I can apply F equals G M1 M2 over R squared. So we are thinking about the product. You're thinking of the product of the two masses, not the mass, right? The product and the distance between them squared. So definitely, inevitably, the force of attraction between these two masses is going to be the same. Okay, look at this uniform ring. If you observe this uniform ring, right, and if you look at the center of it, let's see what the gravitational field intensity at the center is. Just think of placing 1 kg at the center. So remember, when we defined gravitational field intensity, we talked about the force experienced, the gravitational force experienced by a unit mass. The gravitational force experienced by a unit mass, right? That is the gravitational field intensity. So at point A, if I place 1 kg, what is the force experienced by that 1 kg? That is the gravitational field intensity. Deposit, digest all these concepts, right? Then these things will become very easy. Always try to understand stuff in physics. Do not try to memorize it. Get into the core concepts and then develop yourself from those concepts. So what I'm asking is, what is the gravitational field intensity at A? So what is that? Let's see. Now, if you think about this, this is a uniform ring. That means these tiny segments have masses delta m, right? Delta m. It's going to be delta m per unit length, right? If you think about a unit length like this, delta L, it's going to be the same, right? Everywhere in the ring, because this ring is a uniform ring, okay? It's a uniform ring. So if you think about 1 kg and delta m, what can you say? This 1 kg is attracted towards delta m, right? So there's the force of attraction. You can mark that, right? So if you simply think of 1 kg that's placed at A, you can see it's attracted towards delta m with a certain force F. Then again towards this delta m with a certain force F. All around you can see, right? All around you can see it's attracted by the same force, right? Same force. So you can see these forces, right, are going to cancel with each other. On top and at the bottom, left and the right, right? So these forces are going to cancel with each other. So if these forces cancel each other, right, is there any force remaining for 1 kg? There isn't. Therefore, the electric field intensity at A is going to be 0, right? So these kind of observations, I mean, you don't have to hear these things before. You can conclude these things on your own because you know the concept, right? If you just see, I consider 1 kg and delta m, you can apply F equals G M1 M2 over R squared. Okay, if I say the radius of this ring is R, okay, now think about this. G into delta m into 1, right, divided by R squared, right? So you can see F is equal to G delta m over R squared, and it's going to be the same force is going to be there everywhere, right? Like whether it's attracted from the left or it's attracted from the right, the top or the bottom, it's going to be the same. Now I want you to use your imagination and then take this ring and convert it into something 3-dimensional, right? Something like a sphere. of a uniform mass distribution. Now think about that. So the sphere is actually, we are considering a sphere which has cavity, right? In the sense there is no mass inside, but rather in the exterior. So just think of having so many rings like this, and then you are making a three-dimensional sphere. If you think about that, even three-dimensionally, these forces are going to cancel off with each other, right? Three-dimensionally, these forces are going to cancel off with each other. Even if you place another ring out of the whiteboard, okay, or into the whiteboard, right, it's going to be the same, because if it cancels off for one ring like this in the x-axis, it can cancel off in the y-axis, the z-axis, and three-dimensionally, right? Just think logically, you'll find it out. So use your imagination and think, what if you consider a sphere with a cavity, right? Like in the sense just like this, right? But remember, for that to apply, that sphere should be uniform in its mass distribution in the exterior. There's no mass inside, but there's mass outside. It should be uniform. Now I told you, now if you consider a mass m and 1 kilogram here, place 1 kilogram here, mark this point as A, and the distance from mass to point A is r, right? So what is the gravitational field intensity at A? Okay, just forget about gravitational field intensity. What is the force experienced by 1 kg? Yeah, force experienced by 1 kg. What's the gravitational force experienced by 1 kg? That's equal to, F is equal to m into 1, here we have g, divided by r squared. So I don't have to keep on writing this 1 because I'm placing a unit mass in here at point A. Okay, so you can see I can define this force experienced by 1 kg as the electric field, as the gravitational field intensity, right? Gravitational field intensity at point A. So gravitational field intensity at point A is equal to gm over r squared. You can think of it like this as well. If I have mass m and then another mass, let's say mass m1 here, mass m2 here, distance between them is r, F equals g m1 m2 divided by r squared. Now this is the force experienced by m2 towards m1, right? That is the force. But I want to find out the gravitational field intensity at point B. How can I find that out? I know gravitational field intensity at point B is the gravitational force experienced by 1 kilogram that is placed at point B. I have placed m2 but not 1 kilogram. I can do this. I can divide this equation both sides by m2. Then what do I find out? I find out something very interesting. That is, I find that m2 and m2 cancels off and I get F over m2 is equal to g m1 over r squared. What is g m1 over r squared? I know that. That is the gravitational field intensity at B. Then you can see the relationship again between the gravitational field intensity and the force and the mass. So you can see F. So if you don't understand these things, you can pause the video, rewatch this again, take your time. I'm going a bit fast because I'm going to shorten the video. So F over m2 equals EB. So you can see F equals m2 EB. So gravitational field intensity at a certain point multiplied by the mass that you place at that point gives you the force experienced by the mass that you place at that point. Is it clear? Now suppose I have a mass capital M and I want to know what happens to the gravitational field intensity when I get away from mass M. Let's say I want to find the gravitational field intensity here, here, here. Okay, you have the feeling. Okay, greater the distance from mass M, lower the gravitational field intensity, because you know when r increases, when the distance between the mass and the unit mass increases, that means when you move away from the mass M, you know what's going to happen. The gravitational field intensity decreases. You have that perception, right? So now we are going to draw a graph using that intuition, right? Now tell me, right? Suppose I get very, very, very close to mass M. That means R goes towards 0. Like, I'm very, very close to mass m. If I'm 1 kg, just think I'm 1 kg. Suppose I'm very, very close to mass m. So theoretically, I can send this to 0, right? Theoretically, I can send this to 0. If I theoretically send this R to 0, so what happens? Just suppose gm divided by 0.000000000 something, right? And then if you send that theoretically towards 0, so you're reducing R so much. You can understand when this decreases so much, this E increases so very much, right? Have this intuition with you, right? So when you decrease R to such an extent, what happens to the electric field intensity? Mention is over again. So it's not electric field intensity, it's gravitational field intensity. So if you decrease R so much, what happens? The gravitational field intensity increases so very much. Okay, so then you can understand this goes towards infinity. This goes towards infinity, right? But now, you know, like, this is a very important point that I'm going to mention. This is 1 kg, all right? This is 1 kg. You know, 1 kg is attracted towards the mass m, right? It's always an attractive force. It's always an attractive force. I said gravitational forces are attractive forces. So now, if I consider this direction to be positive, can you understand 1 kg is in the opposite direction? It's attracted in the opposite direction. I'm saying this direction is positive, towards the right is positive, but mass of 1 kg is attracted towards the left. So it should exist on the negative side, right? It should exist on the negative side. So that means negative infinity, right? Negative infinity. And now I'm going to tell you this. What happens when R goes towards infinity? That means if you increase R so very much, right? If you increase R so very much, what's going to happen? If you keep on increasing R increases so much that E goes to 0. That the gravitational field intensity goes to 0. So think of putting 10 to the power 5 at the bottom, right? And then squaring it. Yeah, squaring that as well. And just keep on increasing R. Theoretically, you go towards 0, right? So you can see what the variation of the graph is. So from negative infinity, you go towards 0, right? I hope you can understand that. Okay? So remember, this direction has to be considered. So you get negative values for E because E is always an attractive force, and you consider the direction to be positive because I considered to the right to be positive. It could change. If you consider the right to be positive, you get this negative value for E. But if you consider right to be negative, you get the positive value, right? So these are just conventions. So you had always mentioned what you've decided before. So I'm saying to the right is positive. So don't get confused with these things, right? So now I'm considering the other side, the negative side, right? So if this side is positive, I can of course say this side is negative, right? Okay, now just think. So now if you think about the negative side, so this is the negative side, right? Okay, if you think about that, always place that 1 kg. It's so simple. I place the 1 kg. What do you see? I said gravitational forces are attractive forces, so it's attracted towards mass m again. So obvious and so simple, right? Take it easy. So what can you see? It's attracted towards mass m. So now you can see this is the positive side, and okay, the mass 1 kg is attracted towards the positive side. So I have to draw the graph on the positive side, but the R value is negative, right? Because okay, you can see here, these are, okay, from this point onwards R is in the positive direction, but this point onwards R is in the negative direction. So you can see R has negative values but E has positive values, and the same story applies. If I'm very close towards mass m, E goes towards infinity. If I'm very far away from mass m, E goes towards 0. So simple, right? Same story applies. Always try to get the basics and understand, right? Hope it's clear. I'm not going to go into details, right? I'm just going to give you the overall idea of the lesson, because there are so many things to talk about in the lesson. It will take about 2-3 days. So I'm just going to give you a summary almost, right? But with all important theories. Now we define something called the resultant gravitational field intensity. I want to find out the resultant, the overall effect, okay, the resultant gravitational field intensity at point A. Let's say at point A, I want to feel what is, okay, I'm going to place 1 kg at point A because I want to find out the gravitational field intensity at a certain point known as A. So remember, if you want to find out the gravitational field intensity at a certain point, place 1 kg there. That's what I told you before, right? Use that. So I place 1 kg at point A and I am seeing the resultant gravitational field intensity at that point A. So you can see 3 kg is attracting 1 kg, right? Okay, I call this F1, and you can see 1 kg is also attracting 1 kg, and you can see 2 kg is also attracting that 1 kg, right? So I'm not drawing this proportionally, just giving you the ideas. So in reality, we don't know the distances, therefore we don't know what these values of F1, F2 and F3 are, right? So if you think of this distance as R1, this distance, so you have to join the lines, okay, like mass is M1, so mass at A is to be joined with mass here 1 kg, right? So you have to join with a straight line the masses, okay, and then see the distance. So you can call this distance R1, this distance as R2, this distance as R3, okay. So you know how to calculate F1. For example, F1 is equal to G 1 into 3, the product of the mass is 1 into 3 divided by the distance between them squared, R1 squared. So like that you can calculate F2, F3, alright. And now you have learned in mechanics how to resolve these forces. You can get the resultant, right? Okay, that you can do. Suppose these two angles are equal. We don't know if these two angles are equal, but suppose in this example these two angles are equal. That means I'm drawing a line like this, and suppose this angle is equal to this angle. I don't know that, but suppose here it is equal. Then we can see F2 cos theta goes here, F3 cos theta goes here. So the resultant here is going to be F3 cos theta plus F2 cos theta, F3 cos theta plus F2 cos theta, right? And here you can see what's happening. F3 sin theta and what? F2 sin theta, right? And then now for example, now I don't know whether these cancel off. I don't know, right? So for example, if F2 is much larger than F3, then there would be something remaining on the right, okay, to this side. So we have to find out, and F1 is there here. So the direction here, if I consider this direction here, resultant is going to be F1 minus downwards there's, okay, upwards there's F1, upwards there's F1 minus downwards how much? F3 cos theta plus F2 cos theta. I just represent that with capital Y. So F1 minus Y, right? Upwards you have F1, downwards we have F3 cos theta plus F2 cos theta. That I symbolize with Y. Okay, that we found. So we can see here we have F1 minus Y, alright. And if F2 is greater than F3, then I might have a component remaining like this, right? So F2 sin theta is here, and F3 sin theta is here. So if F2 sin theta is greater than F3 sin theta, then you can have this value here, F2 sin theta minus F3 sin theta. So get the resultant of these two. You can draw a parallelogram and see, right? The resultant of these two. You know how to calculate these things. The angle between them is 90, right? So R squared is equal to P squared plus Q squared. R is equal to P squared plus Q squared, square root of that. If you don't know these things, please let me know. I'll help you out, right? So you can take P as F1 minus Y and Q as F2 sin theta minus F3 sin theta, square them, get the square root, you can get the result, right? So this is just an example. I'm going to solve an example here. Suppose 2 kg and 5 kg are kept at a distance of 10 meters apart. So we have 2 kg and we have 5 kg, they are placed at a gap of 10 meters. I want to find out where the neutral point is. That means I want to find out where the resultant gravitational field intensity is equal to 0. That is what we call a neutral point. In a neutral point, the resultant gravitational field intensity is equal to 0. Okay, I just mark point A to be the point where the neutral point is. I just mark it like that, and you should know it's going to be definitely, okay, look at this. Now if you think about the neutral point, where should you think the neutral point should be? It should be closer to 2 kg. Why is that? Why should it be closer to 2 kg? Because look at this equation, you'll understand, right? So you should understand E at A is equal to 0, right? That means if I place 1 kg at A, the resultant force experienced by it should be 0 from the left and the right, right? So if you think 2 kg is attracting 1 kg, so I just mark it as F2, and you can see 5 kg is attracting 1 kg, I mark it as F5. So you should understand F2 should be equal to F5. If F2 is equal to F5, the resultant force at A is 0, right? Okay, then what is F2? Let me know what is F2. If I take this distance as x, right, distance from 2 kg to the neutral point. So A is the neutral point. I am going to take the distance from 2 kg to the neutral point as x. Okay, then tell me, what is F2 going to be? G 2 mass, the product of the masses, 2 into what? 1 divided by, yeah, distance between them squared, x squared. You don't have to keep on putting this 1 here, but for simplicity I put it, but actually electric field intensity is equal to G m over r squared. So you don't have to do that. But for you to understand in this first part of the lesson, I'm just continuing like that, right? So what is F5? F5 is equal to what? G into mass 5 kg into mass 1 divided by, if this distance is x, this distance has to be what? 10 minus x. So 10 minus x squared, right? So you can see g and g cancels off. So you can see 2 over x squared is equal to what? 1, so 5 over 10 minus x squared. So we can see 2 over 5 is equal to x over 10 minus x squared, entire thing squared. If I take square roots of both sides, I get square root of 2 over 5 is equal to x over 10 minus x. So we simplify for x. So if you simplify, root 2 over 5 is 0.632. There might be errors in my calculation, but understand the concepts. So 0.632 into 10 minus x gives you x. Therefore, simplifying this, you can find x to be 3.87 meters. So you can see x is, okay, x is closer, right? You can see the distance to the neutral point is closer from 2 kg. Now why is that? It has to be the case because you know F equals G m1 m2 over r squared. Greater the mass, greater the force. But you should understand F2 should be equal to F5, no, right? You should understand F2 is equal to F5. So 5 kg has a great capacity for a greater force because of its greater mass. But if you have only equal distances, okay, think about it again. So greater the mass, greater the force, right? So if the mass is greater, because we have 1 kg into 5, right, compared to 5, so we have 1 into 5 compared to 2 into 1. If you consider 2 kg, that's 2 into 1. If you consider 5 kg, that's 5 into 1. So you can see 5 kg has a great advantage there for a greater force. So to create a neutral point, you should be a bit far away from 5 kg. If you are far away from 5 kg, that means if you increase the distance, the force is going to decrease. So what we have done is, okay, greater the mass, greater has to be the distance to lower the force. Greater the mass, greater the force. Therefore, to lower that greater force, I have to have a greater distance from the neutral point. Okay, understand this concept, listen over and over again if you did not, and you digest these things, right? Try to think on your own and understand the concepts. Though planets are supposed to go around the sun in an elliptical path, here we are assuming a circular path for simplicity, right? So if you think about the distance from the sun to the planet, as r, right? So you can see that the planet is attracted towards the sun, right? It's attracted towards the sun, and it has what we call a tangential velocity, okay, perpendicular to this force, right? So it has what we call a tangential velocity perpendicular to this force. So with that velocity it goes around, right? So so what is this force? Let's find an equation for this. I can apply F equals ma, right? I'm considering the planet, I'm applying F equals ma towards the sun, right? Okay, can you see F equals ma? All right, so according to that, I know this force F is the gravitational force experienced by the planet. That I can say is equal to G into ms mp divided by the distance between the two objects, that is the sun and the planet, which is equal to r squared, right? Okay, but you know there's another equation, like this is a centripetal motion, right? So the planet is going around the sun, it's attracted towards the sun and it's going like so. So there is a centripetal force towards the sun, so that makes the planet capable of going around in an orbit like this. Without the centripetal force you can't go like that, right? So you know centripetal force can be given by m into v squared over r. So you can see these two forces are going to be equal, because this force, the gravitational force, is the one that provides centripetal force. Without the gravitational force you cannot have the centripetal force, okay? So then if you think G ms mp over r squared, here should I mention mp, the planet, right, is equal to mp v squared over r. So you can see, if I simplify, mp cancels off, right? So what do you get for the velocity? You get square root of gms over r. But you also know v is equal to 2 phi r, the total distance in one round, right, divided by the time period to go around that, right? So this is 2 phi r distance, and the time taken to go around that one complete rotation is t. So if you divide 2 phi r by t, you get the velocity, right? So I can substitute that here, right? So if you think, I can think of v squared is equal to what? Gms over r. That's easier. Then what is v? 2 phi r over t. That entire thing squared is equal to gms over r. Then I can see 4 phi squared r squared over t squared is equal to g ms over r. So you can see the time period, I can take an expression t squared is equal to 4 phi squared r cube over g into ms. So time is equal to, time period is equal to, can take 4 phi squared, square root of that is 2 phi, can take it out, right? Then you have r cube over gms. So you can see t squared is proportional to what? R cube. From this you can see t squared is proportional to r cube. Okay, so t is proportional to r 3 over 2, right? So in questions they can ask, suppose we have the sun here and you are changing the distance of the mass ms from r to 2r. Suppose we change the distance, you are keeping the sun there and you are changing the mass of the planet, right? Okay. So you can see here in the time period, very important observation, in the time period the mass of the planet is not included, so it doesn't depend on the mass of the planet. And if you think about the velocity too, you can see the mass of the planet cancels off, it doesn't depend, right? So if you increase the distance, right, if you increase the distance from the mass of the sun, like you are considering the sun, and you change the distance from the sun to the planet, right? So you can see t is proportional, we are comparing the time periods. You know, t is proportional to r 3 over 2, right? Initial distance is r, so initial time period is going to be proportional to r 3 over 2. Now second time period, right? If you place the same planet at a distance of 2r, hypothetically you placed it at a distance of 2r, then the time period is going to be proportional to r 2r to the power what? Because 2 times the distance, 2r to the power 3 over 2. Then t1 over t2, they can give this for MCQs, is equal to r over 2r to the power 3 over 2. Then you can simplify these things and get expressions for t1 over t2. So like that you can compare the time periods for the different planets, because the sun is the same and you can change the distances, right? So for example, you have the sun and then you have different planets like Mercury, Venus, Earth, Mars, right? And you know the mass of the planet is not included in the expression, therefore you can compare the time periods of different planets. But remember, in reality the planets go in elliptical paths, right? So here we are assuming circular paths, right? You can see, but if the distance from the sun to the planet increases, what happens? If the distance from the planet to the sun increases, time period increases. So when you go from Mercury towards Neptune, time period increases. Okay, so that kind of logic you should have. So suppose I have to find the mass of a planet. How can I do that? Now you know, like if I place a mass m, right, in a position like this, and this is the Earth, and above the Earth I am placing a mass m, and it's experiencing gravity. If I apply F equals ma to that mass m, to the mass m, to the mass m, remember to whom I'm applying, downwards F equals ma. So this force is equal to G capital M simple M over r squared. Now why is that? Why is that r squared? Because compared to the size of the Earth, I'm just placing a mass m on top of the Earth, right? Certain height. But compared to that, compared to the radius of the Earth, right? What is my height, right? Okay, like I'm just going to place a certain mass m on top of the Earth, and the distance between that surface of the Earth and the mass negligible. I'm not going to take it far away into the space, okay? Don't misunderstand. I'm just going to keep it in the surface region of the Earth. So then the distance between the mass m and the center of the Earth is going to be r. Therefore, the force experienced by the mass simple m is equal to Gm m over r squared. So the thing is, when you get away from the spherical mass, right, it's as if the entire mass is concentrated at the center. Actually, this in detail I'm teaching normally because it takes a long time to explain all these theories, but just know, like when I go away from the spherical mass, which is uniform, right, what happens is I can think as if the entire mass is concentrated at the center the moment I step out of this, right? So then Gm simple m over r squared is equal to what? Mg. Why? Because F equals ma, right? So the force experienced by that simple m mass is equal to Gm m over r squared, and the mass of that mass is m, right? And then what's the gravity of that mass? The only acceleration is g, right? So you can see m and simple m cancels. Now you get Gm over r squared is equal to simple g. Now what is the mass of the planet then? Capital M. That's equal to gr squared divided by gm. So gravitational field intensity is g. Can you see that? G is also the gravitational field intensity by Gm over r squared. You can think of 1 kg here, isn't that so, right? So you can see gravitational field intensity, or we can say gravitational acceleration, is equal to Gm over r squared. Is that clear? So then mass is equal to gr squared over gm. Sorry, it's gr squared over capital G, right? Gr squared over capital G. So you can find the mass like that, right? Okay. But remember, this G is the gravitational field intensity at the surface. You can take a distance much greater than this and take 2r. Apply the same logic, right? Place 1 kg here and you can find the gravitational field intensity, right? So it's very simple. The mean density of a planet, you know the mass of the planet now is equal to gr squared over capital G, right? What is the volume of the planet? You can take it as 4 over 3 phi r cube. You're assuming it's uniform, right? And you know the mass is not actually uniformly distributed, but you're assuming that, right? But if you take the mean density of a planet, you just take the mass, right? Overall, you just take the mass and you divide by the overall volume, which is 4 over 3 pi r cube. Then there's not a big issue because you're taking the mean density of a planet. Then you get, if you simplify this, 3g over 4 pi gr. Okay, I'm going to place a satellite, and there's this planet of mass m and a satellite of mass simple m. It's going around the planet. And remember this axis of the satellite, or rather, actually I had my correction, the plane of the axis, the plane, if there's an axis, there's a plane, right, of the axis, is the plane of the axis, is the axis. So the plane of the axis of the satellite should go through the center of the planet. If not, you will understand, if that's not the case, you can't have the motion of the satellite in this way. Just think about it. Because then it's something like this, it's attracted like this, so it's not possible, right? So I'm going to apply F equals ma towards the center of the planet. I'm considering the satellite. I'm applying F equals ma to the satellite, alright? So what's the force experienced by the satellite? Mass m into the mass of the planet into g divided by r squared, right? Very simple. I think you got the hang of it now. Divided by simple r squared, that is equal to mass of the satellite simple m, acceleration a. But you know, what is the acceleration of the satellite? Centripetal force is there towards the center, right? And you know the acceleration is going to be v squared over r, centripetal acceleration. So, or we can think centripetal force is mv squared over r, that is equal to the gravitational force gm simple m over r squared. So you can see certain terms, they do cancel off, right? So you can see gm over r is equal to, the square root of that is equal to v, right? And then you can get an expression for r actually in terms of the time period also. So I'll do that modification. You know, gm over r is equal to v squared over r, sorry, v squared, right? Gm over r is equal to v squared after simplifying. But you know, v is equal to 2 phi r over t. So I can get the square of that, right? Is that clear? Okay, then what do I get? Gm over r is equal to 4 phi squared r squared over t squared. Then I can say, I can take r cube to one side. R cube is equal to gm over t squared, right, divided by what? 1 over 4 phi squared. If I take r, then that is equal to, right, gm, okay, I'm sorry, I've done a mistake here. This t squared should be up, right? See if I'm correct. Yeah, now it's fine. So you can get gm t squared over 4 phi squared, and then you can take 1 over third, the power, right? You know gm is equal to gr squared. Didn't we see that before? We saw that somewhere, right? See, gm is equal to gr squared. G is the gravitational field intensity. So using gm is equal to gr squared, I can substitute that here in gr squared. But remember, this g is the gravitational field intensity at the surface, and r is the radius of the earth, right? If earth is a planet. So gm is equal to gr squared, then into t squared over 4 phi squared 1 over 3. So you can get an expression for the radius of the orbit of the artificial satellite. All right. So you can have something called geostationary satellites. So if you have the satellite that has the plane of the axis along the equator axis, okay, so there's the plane for the equator, okay, this one, and in that plane, if you have the motion of the satellite, and also if the satellite is going in the same direction of the rotation of the earth, and also if the satellite has the same time period of the earth, we can have what we call geostationary satellites. So always we will have the geostationary satellite on top of the earth at a certain location, specific location. So I'll stop here. There's the energy part of gravitational fields. I will do that on another day. Thank you.